Hello and welcome. My name is Richard Corden. I'm the lead software developer here at Programming Research, and today I'd like to show how upgrading to C++11 can help improve the quality of your software. First, I'd like to give a brief background on Programming Research. We provide static analysis solutions targeting safety critical, mission critical, and commercially critical software. Our strength lies in our language knowledge, specifically in C and C++. We're voting members of the ISO C++ committee, and we use this to help us identify vulnerabilities and come up with best practices for safe language use. As a result of this, we produce coding standards. We're founding members of both MISRA working groups, and as a result of all of this, both the language knowledge and coding standard knowledge, we use this to develop our static analysis technology that helps provide automation and scalability to the developers at the sharp end. My focus in programming research is on the C++ side. I represent programming research on both the ISO C++ committee and the MISRA C++ working group. My day job is taking all of this and implementing QA C++, which is our static analysis tool for the C++ language. My objective today is to provide a list of features that can be used to help improve your code quality. I can do this by showing how it helps reduce implementation-defined or unspecified behavior. And most importantly, it allows you to say what you mean, which also helps with the maintainability of the source code. I expect that the talk is going to be about 20 minutes. I've got about 6 topics, and each topic I'm going to provide a little bit of background on the general construct within the C++03 standard and how it's changed in C++11. I'll show in some cases how little tricks or handshakes existed against the old feature and how those are now redundant with the new language feature, with the new version of the language feature. As well as providing this information, I also have some source code and some examples that demonstrate this in the real world. The first area I'd like to talk about relates to strongly typed enums. So in C++03, the initializer for an enumeration is actually, the type of it is actually unspecified. And this can lead to situations where it's not clear what the subsequent values of enumerations are. Another problem with C++03 enums is that its implementation defined what the type of the enum is within the compiler. It only needs to be large enough to be able to store all the values. The final issue with enums in O3 relates to the fact that they can implicitly promote to arithmetic types, and this might lead to surprising situations where an enum can appear in some arithmetic expression. So C++11 addresses these problems by allowing the user to specify the underlying type, and also by disabling the implicit conversion to arithmetic types. So now I'd like to show you an example of this. Here is some source code. I have a couple of examples, and this is just using our message browser to show the annotated source with the output from QA C++ over the source code examples. So for our strongly typed enum case, here we can see we have the definition of our enumerator, and we have an initializer here. And as I said, the type of this initializer is unspecified. So we don't actually know what the value of E3 is. It may actually be -1, or it could actually be some very large integer. Similarly down here, we have a variable being used in an arithmetic expression. And again, it's not clear at this case, because our enumerator can implicitly promote to int or to an integral type. It may not be noticed that instead of referring to EL, we're actually referring to E1 in this arithmetic expression. So C++11 solves both of these problems. First of all, by allowing us to specify the underlying type of our enumeration. So now we know exactly what the values are of our enumerators. And secondly, we can actually create a scoped enum, which means that this conversion, the promotion to int, is no longer allowed, and we can see here that we have an invalid arguments to operator message from QA C++, basically highlighting that the code isn't valid. The second example we'll touch on is explicit conversion operators. So many coding standards simply ban user conversion operators completely. And the motivation is basically that when somebody reads the code, it's unclear exactly what the code is doing. You can't just look at a piece of code and know what's happening, since there may be conversions taking place. However, a really nice place, or conceptually a nice place to use user conversions relates to a true or false checking on a type. Is this type valid or not? So a sort of a obvious mistake to make is to add an operator bool to the type which returns true if the object is valid and false otherwise. But the problem with bool is that as it is an arithmetic type, it'll mean that our object can be used in an arithmetic expression, which is very unlikely the desired functionality. So C++ addresses this by reusing the explicit keyword for conversion operators in a very similar way to how it is used for converting constructors. So again, we'll show some examples of this. So here we can see we have a class A, and we've got our conversion operator going to bool. And we have the desirable case here. We've got if A in our context here. So A calls the conversion operator and tests it for true or false. And here we have the undesirable case. And we can see that we don't want the conversion to happen here, but there's actually no way to tell it not to happen. Although there is a way to tell how it might happen. So what we can do now is we can use some special handshakes to come up with a particular kind of type that can be used to test for true or false, but that can't be used in an arithmetic context. And there's one such type within the language, which is a pointer to member. So here we can see that we're creating the conversion operator that uses a pointer to member type. And we can still use this in our if condition, but we're no longer able to use this in our arithmetic condition. However, it requires that both, first of all, it requires somebody to actually know about this in order to add it to their code, and it also requires that everybody reading and maintaining the code also knows what this is doing. So in C++ 11, these problems have been addressed with the addition of the explicit keyword. And we can see here now that we go back to the same example as for the first case, just simply with explicit operator bool. Very obvious, we know exactly what it means. We get the conversion happening on the if condition, but we don't have any conversion happening in the arithmetic context. Another favorite area in coding standards relates to virtual functions. So many coding standards would recommend that if you have a function in a derived class that's implicitly virtual because it's overriding a base class virtual function, then the virtual keyword should be added to improve the clarity. This works from a maintenance perspective or a documentation perspective. However, it doesn't add any extra enforcement on behalf of the compiler. And a change to the signature of the base class member won't result in a compile error, but it will result in the semantics of the program changing. In C++ 11, a new meaning has been given to the override. It's now called a special identifier, and this helps us address the problem. So just to demonstrate the problem again, so here we have our base class virtual function, and we have our message relating to our coding standard that tells us that this is implicitly virtual, and so historically we would have recommended adding the virtual keyword for documentation. So our developer here has added these virtual keywords, but unfortunately in the meantime, the base class member function has now been made as a const member, so its signature has changed. The problem now is that this derived class function no longer overrides the base class function because the signature is different. So QA C++ is highlighting this to us by pointing out that this function is actually hiding the base class function rather than overriding it, in which case it wouldn't be any message. So now we can look at the C++ 11 solution. We can now add the override keyword onto our derived member function. This tells tools such as QA C++ and also the compiler that this function must override a base class virtual member. And because it doesn't, we now get a new message highlighting that this function is not overriding a base class member. And a similar message will be generated by your compiler. Another favorite area of coding standards relates to the contract or the definitions provided in a default implementation of a class. So, the explicit declaration of copy functions, etc. The general idea is that from a class without a copy constructor or copy assignment operator, it's not clear to the maintainers of the class if those functions are ever used or ever needed. But the problem with adding these functions is that the semantics are changed slightly in the class. Another issue is if the implementation is provided, then there's extra code added, and as a general rule, more code equates to more bugs. And finally, because the functions have been added, there are actually fewer optimization possibilities, as the compiler may be able to work out that it can do slightly more performant code in the case that it knows exactly how something is going to be copied. So C++11 addresses this problem by reusing the default and delete keywords and allows us to add in special definitions on these member functions. So now we can show an example of this. So here we can see we have our basic class, and as I was saying, it's not clear if this class should be copied or if it shouldn't be copied. It's not, from somebody looking at this, we don't know exactly whether that functionality should be enabled or not. So we can see here that our user has come back and he's obeyed his coding standard advice. So the first thing he's done is he's declared the assignment operator as private so that it can't be called from outside of the class. And he's given it a void return type so that it can't be used maybe in the way we would think it should be used. And the second thing he's done is he's explicitly defined the converting constructor, as we obviously want to allow that the copy constructor to be used. So he's explicitly defined the copy constructor, copying the single member. And as we can see here, this is not necessarily ideal because this definition is exactly the same as the definition that would be provided by the compiler. So if we were to add a new member to the class, then that member, we would also have to remember to add that member to the initialization list. Otherwise, we'd add a problem into the code. So if we now look at how C++11 has solved this, the first thing that we can do is we can specify that the copy constructor equals default, meaning that its definition should be the default definition. And the second thing we can do is say that the assignment operator should be equals delete, meaning that it shouldn't be called. And if somebody attempts to call this function, then the compiler will issue a message highlighting that it can't be used. Another interesting change with the C++11 standard is the changing of auto from a storage class specifier to a type specifier. And one of the main benefits of this is the simplification in terms of declaring functions and objects. One of the problems with member functions, especially when they're being defined out of line, is the need to explicitly qualify the types that are in the class and are used as return types. So here we can see we have a function foo with a return type, which is a member of the same class, and we have to specify that return type twice, once for the return type and once for the function. In the case of templates, this is even worse, as we also need to tell the compiler that this is a type name, so we need to include the type name keyword. So now we can see that because auto is a type specifier, it allows us to simplify this code quite significantly. So here we can see the traditional C++03 version. So we have our function definition and we have our return type. We've told the compiler that it's a type. We have the qualification again for the identifier foo. And note here that we don't need to qualify the parameter type. And the reason we don't need to do this is that as we know we're defining foo, we know to look up this name in the class in temple class T. So we don't need to have the qualification here. Another example here is just in the body of this function, we need to specify that this qualified name actually refers to a type in order for us to be able to declare an object. So we have to specify that iterator is in fact a type. And you can see now that we have two messages from QA C++ highlighting that these can be improved with C++11. So if we look at the C++11 version, we can see here that we're using auto as the return type placeholder, and then we provide the return type on the right hand side after the parameter list. And so here we have again auto as the placeholder, we have the qualification for the name of the function, the parameter list, and now we have the return type. And as for the parameter previously, because we know we're defining the function foo, the compiler now knows to start looking up for type in the scope of temple class of T. And here you can see we can also just declare iter. We can say auto iter, and its type will be deduced from the type of its initializer, in this case to be s : iterator. The final example I'm going to talk about relates to a combination of two features in C++11, specifically variadic templates and OR value references. Variadic templates are basically a type-safe ellipsis parameter. They allow many cases, but A basic usage is where a function can have variable number of parameters passed in, all type safe, all with the correct type. A special version of OR-value references, which has become known as universal references, allows for perfect forwarding. And these features together provide that objects can be constructed just once, but when they're constructed in the right way. So I'm going to give you an example of this using shared pointer. So here we can see we have a class A, which has a couple of members. And as I say, with Variadic templates, this could be any number of parameters, any number of members. We declare a type def for our shared pointer. And historically, this is how we would create a new object and create a shared pointer to it. So we allocate memory for our object A, passing in the 10 and 20 for the parameters. This newly allocated memory is then passed into the shared pointer constructor. And as part of its implementation, the shared pointer will also allocate a reference count. So in order to create a single shared pointer, there will actually be two allocations, one for the object itself and one for the reference count. The combination of universal references and Variadic templates means that we can now use a function called makeShared. This function allows for any number of arguments, and it will basically pass them straight through to the constructor. Because the arguments have been passed straight through, makeShared can also just perform one allocation, and that single allocation can be large enough both for the object itself and for the reference count. So now we have a single memory allocation followed by the construction of the object A directly into the memory as needed. So just to wrap up, I hope I've shown how C++11 addresses some of the common pitfalls in O3 and removes the need for developers to learn some non-intuitive workarounds. We've looked at 6 specific examples that demonstrate the day-to-day impact of these changes on the developer. And finally, I hope too that I've been able to demonstrate how our tool can be used to auto-detect problems with either standard, as well as reduce the risk in migrating from C++03 to C++11. If you'd like some more information, then you can contact us on our website, programmingresearch.com. But why not try a version of our tool? So you can get this, you can go to programmingresearch.com trial and download both the QA C++ tool and also our other tools. I'd like to thank you very much for your time.